Hello everyone, I hope all of you are doing well. So now we are talking about 14.8, which is Lagrange multipliers. Lagrange multipliers, and how is it related with 14.7 that we studied about extreme values. We can say that the extreme values that we had, which is talking about max, min, and saddle point in 14.7, we were finding the maximum of something, the minimum of something throughout the whole domain without having any conditions on the function that we had. For example, you are having a business of selling things and you want to have a maximum profit, so you're using this idea that we have studied in 14.7. Or when your business is construction and you want to minimize the cost, we are using the idea that is given in 14.7 if there are no conditions in the business that we have got. When we are talking about Lagrange multipliers, we are having constrained maxima and minima. So the maximum and the minimum that we are finding is constrained. That means we have got conditions here. How is that? For example, you have got a new medicine and you are giving it to a group of people with diabetes, and you want to find its maximum effect on those group of people. How is it working? Is it affecting well, or is it affecting badly on them? That is a general case. But if you say, I'm giving this new medicine to that group of people, but I have got conditions since the group of people that I'm checking this new medicine on have got heart disease, for example, kidney disease, or any other disease. So you have got conditions here. You cannot just check the maximum effect of that new drug on the new patient, on the patients with diabetes. You have to also consider the cases, the conditions that we have got. Some of the patients having heart disease, kidney disease, and so on. So that's called constraint maxima and minima. Here in the first two examples, it is required from you to find the closest point to the origin, but it is explained in another way. Like there is another method used in here, but that method that is used in example 1 and 2 is not it's not holding, it's not satisfied for every example that will be given to you. So I'm directly jumping to the idea of Lagrange multipliers, okay, the method of Lagrange multipliers. And for example 1, I'm directly using that method of Lagrange multipliers instead of studying that method that is given there for the first two examples, and they are not good for every example. So here the method of Lagrange multiplier, what does it say? It says, suppose that you have got a function f, okay, and you have got a function g. Those functions are both differentiable, and we have got that grad f is not equal to 0 when g of x, y, z is equal to 0. So the conditions are obvious. F and g are continuous and differentiable, of course. And we have got the function g is equal to 0 with the condition that the grad f is not equal to 0. To find local maximum and local minimum according to that constraint of g, okay, so we are finding max and min for f with the condition that we have got g is equal to 0. We have to find the values of x, y, z, and lambda that simultaneously satisfy those equations that we have got here. So grad of f is equal to lambda grad of g, and we have got the condition that g is equal to 0. So for finding maximum and minimum values for a function f with the condition g given to you, we are using this equation, okay, and that equation. We have to solve the examples, the exercises that we have got using grad f is equal to lambda grad g with the condition that g is equal to 0. So moving back to the first example, let's see what is required from us and how we use Lagrange multipliers to find maximum or minimum value that is required. So here, the example that we have got, it says find the point P of x, y, z. So it is required from you to find a point that is in a three-dimensional space that has got x, y, z on the plane 2x plus y minus z minus 5, that's equal to 0, and with the condition that we have got this one is equal to 0, that is closest to the origin. So this is the function that we have got. What does that mean here? That means we are finding a point on that plane that is closest to the origin. We are minimizing the distance here. Here, this idea means minimize the distance with the condition given to you that g of x, y, z is equal to 0, because the point that we are finding is on that function g. Okay, let's come to analyze the question that we have got and find the maximum and minimum value that is the minimum value that is required from us. So here we want to minimize the distance. And how is the distance described in general? If you remember, distance formula is equal to what? Is equal to x minus x naught, which is origin, because we are finding the distance between the plane and the origin. So it becomes x minus 0 squared plus y minus 0 squared plus z minus 0 squared. This is the distance formula, and this is the function that we have got, which we want to minimize it. Okay, so this function is to be minimized, that is given to you here. Instead of minimizing this function, since it has got square root in it, sometimes it's making the problem harder for us. Instead of minimizing that one, we are simply minimizing this function, this distance function. Why? Because minimizing this distance function, f, like that, it's the same thing as if we minimize that one, x squared plus y squared plus z squared under the square root. Why? Because that f that we have got is strictly increasing. Okay? So the only case that we can remove something, that we can change the function that we have got to something else, is if f that we have got is strictly increasing. If we do not have this condition, we cannot remove that square root and work on the function x squared, y squared, z squared instead of that one that we have got. So we are removing that square root because the function is strictly increasing, or else we cannot remove that square root on it, and we have to work on it with the square root. But here, thankfully, that the function that we have got is strictly increasing, so working on this function without the square root will be easier. So what is our aim? Our aim is that we have to minimize this function with the condition that g of x, y, z is equal to 0. How do we do that? Using Lagrange multipliers. Now I'm going to start with the Lagrange multiplier. What is the condition saying? It says that grad of f is equal to lambda grad of g. What is grad of f? We have studied this one previously. Grad of f is equal to 2xi, okay, the derivative of the function f with respect to x, derivative of function f with respect to y, okay, plus the derivative of the function with respect to z. That must equal to what? That must equal to lambda multiplied with grad g. What is grad g? Again, derivative of g with respect to x, y, and z. So with respect to x, it becomes 2i. With respect to y, it becomes j. And with respect to z, it is equal to minus k. Okay? So we have got an equation, and those two equations are equal to each other only when we have got 2x is equal to 2 lambda, Okay, so here we get that x is equal to lambda, and they are equal to each other if 2y is equal to lambda. So lambda here is equal to what? Is equal to, sorry, y, not lambda. So y here is equal to lambda over 2, and we also must have 2z is equal to minus lambda. So from here we get that z is equal to minus lambda over 2. So we found x, y, z using Lagrange multipliers, okay? But the value of x, y, z that we have found is in terms of lambda, so we have to find lambda. How do we find lambda? Well, we have got the condition that g of x, y, z is equal to 0. So instead of each x, y, z that is given in the g, we are substituting that x, y, z that we have got in terms of lambda to find the value of lambda, and then we will get the values of x, y, z. So this one is true, okay, with the condition that g of x, y, z is equal to 0. So what do we get? We get that 2 multiplied to x is lambda, okay, plus y, we have got it is equal to lambda over 2, minus z is minus lambda over 2, minus, of course, 5 we have got from the function, that's equal to 0. Here we get that this is 2 lambda. This part becomes lambda over 2 plus lambda over 2 becomes 2 lambda over 2. So it becomes plus lambda is equal to 5. Okay, I'm taking 5 to the other side. So from here we get lambda is equal to 5 over 3. So since we got that lambda is equal to 5 over 3, we know that x is equal to lambda. So from here we get that x is equal to 5 over 3. Okay, and again y is equal to what? Instead of lambda we put 5 over 3. 5 over 3 over 2 gives me 5 over 6, and z is equal to minus lambda over 2, so that gives me minus 5 over 6. So what do we get? We got x, y, and z. P of x, y, z, the point that we found, is equal to what? Is equal to 5 over 3, 5 over 6, and minus 5 over 6. And this becomes the point which is on the plane g of x, y, z, and this point is closest to the origin. So this is how we find the minimization. Here we minimize the distance between that plane G with the origin using Lagrange multipliers.